A galaxy's heart holds a secret so powerful it governs every star. That force is a supermassive black hole, a cosmic monster whose mysteries we are just beginning to understand. By the end of this journey, you will know 28 incredible secrets about these dark giants, from their violent births to their ultimate control over the cosmos. We will explore how they warp space, tear stars apart, and might even dictate where life can form. What single cosmic mystery most captivates your imagination? Their sheer size defies any earthly comparison. A typical supermassive black hole can weigh in at millions, even billions of times the mass of our own sun. Think of our entire solar system, from the sun out to the distant cloud of comets, all that space and matter. Now crush it, condense that staggering amount of mass into a single point, a region of space so small and so dense that its gravitational pull becomes inescapable. This is the reality of the monsters at the center of galaxies. Their gravity is so profound that it doesn't just pull on nearby stars, it actively sculpts the entire core of the galaxy. Stars in the galactic center are forced into a frantic, high-speed dance, whipping around this invisible anchor point at velocities that would fling them out into the void if not for its overwhelming hold. This gravitational dominance warps the very fabric of the universe around it, bending the path of light and stretching the flow of time in ways that challenge our fundamental understanding of physics. How do you even begin to measure something that can swallow light itself? Their immense scale presents a puzzle that reaches back to the dawn of time. How did these gravitational giants form so quickly after the Big Bang? We find supermassive black holes already in place, fully formed, when the universe was just a toddler of a few 100 million years old. This leaves scientists with a cosmic race against the clock, and two leading theories attempt to explain it. The first is a story of a spectacular single event. In the primordial universe, vast clouds of pure hydrogen and helium gas, undisturbed by heavier elements, could have gathered in incredibly dense patches. Under their own immense weight, these clouds might have skipped the entire process of star formation entirely. Instead of fragmenting into many stars, such a cloud would have collapsed directly, catastrophically, into a single, massive black hole seed, one that could be tens of thousands of times the mass of our sun from its very first breath. The second theory suggests a more gradual, yet incredibly rapid beginning. Smaller black holes, the remnants of the first generation of colossal stars, could have served as seeds. These seeds would have needed to gorge themselves on the surrounding gas and dust at a ferocious, almost impossible rate to reach supermassive status so early. This presents a major challenge, as a feeding black hole creates intense radiation pressure that should push material away, effectively turning off its own food supply. How did they overcome this cosmic diet limitation? The truth might be a combination of both paths, a frantic scramble for mass in the chaotic infancy of the cosmos. This name, black hole, is perhaps the greatest misnomer in all of science. They are not holes in the fabric of space, not cosmic potholes waiting to be filled. The reality is far stranger and more profound. A black hole is an object of almost unimaginable density. Picture the entire Earth, all its mountains, oceans, and cities, crushed into the size of a single marble. That level of compression barely scratches the surface of what happens at the heart of a supermassive black hole. All that millions or billions of solar masses of material is compressed into a single, infinitely dense point known as a singularity. This is the true core of the beast, a place where the laws of physics as we know them break down completely. Surrounding this incomprehensible point is the event horizon. Think of this not as a solid surface, but as a one-way membrane, a boundary in space-time from which nothing, not even a single photon of light, can ever return. It is the ultimate point of no return. If you were to cross this invisible threshold, the gravitational pull from the singularity would become your inescapable reality. The force on your feet would be so much stronger than the force on your head that you would be stretched into a long, thin stream of atoms, a process scientists call with grim humor spaghettification. So while we call them holes, they are really the most extreme concentrations of mass and gravity in the entire universe. How does something with no physical surface exert such total control over its surroundings? This boundary of no return, the event horizon, is the ultimate one-way street in the cosmos. Once an object crosses this invisible line, its fate is sealed. No force in the universe can pull it back, not even the speed of light itself. The event horizon marks the point where the black hole's gravity becomes so overwhelming that the escape velocity exceeds the cosmic speed limit. It is a place where the very concepts of space and time swap their roles. Outside the event horizon, you can move through space freely, and time marches forward as it always has. But cross that threshold, and all paths through space lead inexorably inward toward the central singularity. Your future is no longer your own. For decades, this was a purely theoretical frontier, a line drawn by mathematics. Then, in April 2019, a global collaboration of telescopes, acting as a single Earth-sized instrument called the Event Horizon Telescope, unveiled the very first visual evidence. That now iconic fiery ring of orange and yellow is not the event horizon itself. We cannot see that. What we are witnessing is the black hole's shadow, silhouetted against the incandescent glow of matter being superheated as it spirals into the abyss. The light from that frenzied accretion disk bends dramatically around the event horizon, creating a perfect circle of darkness, a shadow that confirms the existence of this ultimate point of no return. We are no longer just imagining these cosmic monsters. We are staring directly at their dark hearts. What other secrets will come into focus as we push our vision even further? This invisible boundary hides a force that warps reality itself. The closer you drift toward a black hole, the more you experience its tidal forces. These are not ocean tides, but a difference in gravity's pull. Think of gravity not as a single force, but as a gradient. The part of you or any object that is closer to the black hole feels a vastly stronger gravitational tug than the part that is farther away. Near an object as dense as a black hole, this difference becomes catastrophic. If you were to approach feet first, the gravity pulling on your feet would be exponentially stronger than the pull on your head. You would begin to stretch slowly at first, then with increasing violence. This is spaghettification, the process of being stretched into a long, thin stream of atoms. It is not a quick end. Long before you reach the event horizon, you would be pulled apart, molecule by molecule, into a single strand of elementary particles. Even a sturdy spacecraft would suffer the same fate, its metal hull and framework offering no resistance against this ultimate stretching force. The material that was once you would then spiral inward, heating to incredible temperatures and adding to the black hole's final mass. This gruesome process is a direct consequence of the intense, localized gravity that defines these cosmic monsters. It forces us to ask a chilling question. What other realities, equally strange and violent, govern the final moments before crossing that final line? This cosmic stretching force is not an isolated phenomenon. It is part of a much grander relationship, a hidden dialogue between the black hole and its entire home galaxy. For a long time, astronomers thought of galaxies and their central black holes as separate entities, one simply living inside the other. But a startling discovery revealed a deep, fundamental connection. The mass of a galaxy's central supermassive black hole is almost perfectly proportional to the mass of the galaxy's central bulge, that dense, spherical swarm of stars at its core. A larger bulge always hosts a more massive black hole. This correlation is too precise to be a coincidence. It tells us that the growth of the galaxy and the growth of its dark heart are inextricably linked. They grew up together, shaping each other's destinies across billions of years. This is the sixth secret, a story of co-evolution. How could a single object, invisible and relatively tiny compared to the vast galaxy, exert such influence? The answer lies in the black hole's feeding habits and its ultimate power to self-regulate. When a black hole feasts on too much gas and dust, it doesn't do so quietly. The infalling material forms a searingly hot accretion disk, and this process unleashes a titanic outburst of energy. These are not gentle glows, but roaring quasars and powerful jets that can blast across space for thousands of light years. This energy flooding out from the center acts like a cosmic thermostat. It heats up the surrounding gas, preventing it from cooling down and collapsing to form new stars. In the most extreme cases, it can even blow that gas completely out of the galaxy, cutting off the fuel supply for future generations of stars and effectively starving the black hole itself. This violent feedback loop means the black hole can put a limit on its own growth and on the growth of the galactic bulge around it. They are locked in a gravitational dance, a push and pull that ultimately determines the final size and shape of the galaxy itself. Our own Milky Way, with its relatively quiet central black hole, is a product of this ancient, balanced relationship. What happens when this delicate balance is violently broken? Our own galactic backyard holds a similar dark heart, a story pieced together not by seeing the unseen, but by watching its gravitational handiwork. For decades, astronomers trained their telescopes on the crowded, dusty core of the Milky Way, patiently tracking the movements of a handful of stars. These were not ordinary stars drifting through space. They were caught in a frenetic, high-speed dance, whipping around an invisible focal point at thousands of kilometers per second. Their paths were not random. Each one traced a perfect elliptical orbit around absolutely nothing. The most famous of these, a star called S2, became a key witness. Its orbit revealed an astonishing truth. It swings so close to the invisible center that it completes a full loop in just 16 years, reaching speeds of over 3% the speed of light at its closest approach. By meticulously charting these stellar orbits, just as Kepler did for the planets around our Sun, scientists could calculate the mass of the object holding them captive. The math was undeniable. Something with a mass of over 4 million suns was crammed into a region of space smaller than our solar system. The only possible object that could be so massive and so small was a supermassive black hole. We now know it as Sagittarius, a star, the silent, dark giant governing our galactic home. This discovery transformed our understanding from theoretical speculation to confirmed reality. We live in the gravitational domain of a cosmic monster, one that is currently quiet, but whose past may have been far more violent. What other stellar dancers might reveal the hidden history of our galactic center? But that quiet giant in our own galaxy is the exception, not the rule. In the deep past, the cores of most galaxies were not silent. They were the sites of the most violent and luminous events in the entire cosmos. We call these brilliant beacons quasars. For years after their discovery, quasars were profound mysteries. They appeared as star-like points of light, yet their spectra revealed they were impossibly far away, billions of light years distant. To be visible from such a staggering distance, they had to be emitting almost unimaginable amounts of energy. A single quasar can outshine an entire galaxy of hundreds of billions of stars. The question was, what cosmic engine could possibly produce such power? The answer lies in the very object we have been discussing, but in its most ferociously active state. A quasar is not the black hole itself. It is the black hole's accretion disk, a vast, swirling maelstrom of gas and dust, heated to incandescence as it is devoured. Imagine a storm of matter larger than our entire solar system, spiraling inward at nearly the speed of light. The friction within this disk is so intense that it heats the material to millions of degrees, causing it to glow with the fury of 1 trillion suns. This is the true nature of a quasar, a supermassive black hole in the act of feeding. Its brilliant accretion disk so bright it drowns out the collective light of every star in its host galaxy. These are the beacons of the young universe, a time when galaxies were rich with gas and their central black holes feasted with abandon. They represent a phase that most large galaxies, including our own Milky Way, likely went through in their youth. Their incredible brightness allows us to see them from the edge of the observable universe, giving us a direct window into the chaotic and energetic processes that shaped galaxies in their infancy. What happens when such a brilliant beacon finally runs out of fuel and its light fades away? Yet even a quasar's blinding light is not the final expression of a black hole's fury. Some of these cosmic engines unleash their energy in a far more focused and violent manner, shooting out colossal beams of matter that can stretch for millions of light years. These are the powerful jets of active galactic nuclei. Imagine a supermassive black hole spinning at a significant fraction of the speed of light, its intense gravity dragging the very fabric of space-time around with it. This rotation, combined with incredibly powerful magnetic fields generated by the churning accretion disk, acts like a cosmic particle accelerator. Not all the material falling toward the black hole crosses the event horizon. A fraction of it gets channeled and focused along the black hole's rotational poles, launched outward at nearly the speed of light. These jets are composed of superheated plasma, a searing soup of subatomic particles and magnetic energy. They punch straight through the surrounding galaxy and roar out into the vast, empty space between galaxies. Their influence is staggering. These jets can heat the sparse gas that exists in galaxy clusters, preventing it from cooling and collapsing to form new stars. They carve out enormous cavities in the intergalactic medium, acting as cosmic regulators on a scale almost too large to comprehend. We can sometimes detect them through the radio waves they emit, appearing as two brilliant opposing lances extending from a galactic core. They are a testament to the fact that a black hole is not just a consumer but also a creator, a sculptor of the large-scale structure of our universe. How does an object known for its ultimate darkness become one of the brightest and most powerful sources of energy we can observe? That silent darkness at the center of a galaxy can hold a hidden storm of motion. The 10th secret reveals that many supermassive black holes are not static pits but cosmic whirlpools, spinning at velocities that approach the ultimate speed limit itself. This rotation is not like a planet or a star where a solid body turns. A black hole has no physical surface to spin. Instead, its immense gravity causes the very fabric of space and time around it to be dragged into a vortex. This phenomenon is known as frame dragging. Imagine space-time as a vast, still sheet. A non-spinning black hole would be like a heavy weight simply creating a deep dip in that sheet. But a spinning black hole is like that same weight set into a violent whirl, twisting the entire sheet around with it. Anything close to this rotating monster, even light, is forced to move in the direction of the spin. It is as if the universe itself is being stirred. This spin is not just a curious detail, it is a fundamental source of power. The rotational energy of a spinning black hole, harnessed by its incredibly strong magnetic fields, is the primary engine for those colossal jets we see erupting from active galaxies. When infalling matter is caught in this twisted space, the magnetic fields can funnel some of it away from the event horizon and launch it outward along the spin axis at nearly the speed of light. The faster the black hole spins, the more energy is available to fuel these cosmic cannons. A black hole's spin is its final, unique fingerprint, a record of its entire violent history, written in the swirling fabric of reality. What does the spin of our own galactic giant tell us about its ancient past? This record of spin, written in twisted space-time, leads us to a deeper mystery, one that challenges our most fundamental understanding of reality. The 11th secret confronts the black hole information paradox. At its heart is a simple yet devastating question. What happens to information when it falls into a black hole? In our everyday world, information is never truly lost. If you burn a book, the ashes and smoke still contain, in principle, the information about every word and letter, even if it is impossibly scrambled. The laws of quantum mechanics insist that information must be preserved, but a black hole seems to break this cardinal rule. Anything that crosses the event horizon, whether a star, a spaceship, or that book, is lost forever to the outside universe. Its mass, its charge, and its spin are added to the black hole, but every other detail about it, every unique arrangement of atoms that made it what it was, appears to be permanently erased from existence. This creates a paradox, a direct conflict between Einstein's theory of general relativity, which governs black holes, and the quantum laws that rule the subatomic world. For decades, physicists believed this information was simply gone. Then, Stephen Hawking made a startling discovery. He realized that black holes are not completely black. Empty space, according to quantum theory, is not truly empty. It is a seething foam of virtual particles, pairs of particles and their antiparticles that constantly pop into existence and then annihilate each other almost instantly. Hawking proposed that when this happens right at the edge of the event horizon, a strange theft can occur. One particle of the pair falls into the black hole while its partner escapes into space. To conserve energy, the particle that falls in must have negative energy, which effectively reduces the black hole's mass. The escaped particle becomes real, carrying away a tiny bit of the black hole's energy. This is Hawking radiation, a faint whisper of particles slowly leaking from the black hole. Over unimaginable eons, this process causes the black hole to lose mass and eventually evaporate completely. But here lies the core of the paradox. The Hawking radiation that escapes is random. It carries no information about what fell in. So when the black hole finally vanishes, all the information about everything it ever consumed vanishes with it, seemingly violating a fundamental law of the universe. This paradox suggests that something is profoundly wrong with our current physics, that a deeper theory, one that unifies gravity and quantum mechanics, must exist. The slow, cold death of a black hole through Hawking radiation might hold the key to the next great revolution in our understanding of the cosmos. If information cannot be lost, then where does it all go? That paradox at the event horizon is just the beginning of the strangeness. Crossing that invisible boundary would plunge you into a realm where physics as we know it ceases to exist. This is the 12th secret, the bizarre reality inside the event horizon. From the outside, we see a dark sphere, but once you cross it, the true nature of the black hole reveals itself. The most profound change is the inversion of space and time. Outside, you can move freely through space but are forced to move forward in time. Inside the event horizon, all paths through space lead inexorably downward toward the center. Your future is no longer a matter of choice. It is a single, predetermined destination, the singularity. Moving away from the center becomes as impossible as moving backward in time is for us. You are on a one-way slide to the heart of the beast, and at the end of that slide lies the greatest mystery of all, the singularity itself. This is the point where all the black hole's mass is crushed into an infinitely dense, infinitely small point. Our equations of general relativity predict its existence, but they break down completely here. Concepts like space and distance, even cause and effect, lose all meaning. The laws of physics simply do not apply. This tells us that general relativity is an incomplete theory. It cannot handle such extremes of gravity. To understand the singularity, we would need a theory of quantum gravity, a way to marry the vast scales of Einstein's universe with the fuzzy rules of the quantum world. Without it, the center of a black hole remains the ultimate unknown. Some theories speculate that the singularity might not be a point, but a bridge a wormhole connecting our universe to another part of spacetime, or even to a completely different universe. This idea is mathematically possible, but it is almost certainly not a passage any object could survive. The immense tidal forces and the bizarre physics at the core would likely destroy anything long before it could complete such a journey. The interior of a black hole is the final frontier of our understanding, a place where mathematics points to realities beyond our current imagination. What new laws of physics are waiting to be discovered in that ultimate darkness? That silent darkness we just explored can erupt into a spectacle of cosmic violence when a star makes a fatal mistake. The 13th secret reveals the dramatic feeding process known as a tidal disruption event. This is the moment a star, wandering through the chaotic core of its galaxy, strays too close to the gravitational influence of the supermassive black hole. The difference in the pull of gravity on the near side of the star versus its far side becomes overwhelming. The black hole's tidal forces, the same that would spaghettify an astronaut, now grip an entire sun. The star is stretched horizontally and compressed vertically, pulled into a long, thin strand of incandescent gas. It does not just break apart quietly. It is violently shredded, its material unraveling in a process that takes only hours or days. The star's own nuclear fusion cannot hold it together against this ultimate gravitational assault. But the destruction is only the beginning of the show. The stellar debris does not simply vanish into the black hole all at once. Conservation of angular momentum flings much of it into a chaotic, elliptical orbit, forming a temporary, superheated accretion disk around the event horizon. As this disk of what was once a star spirals inward, it is compressed and heated through friction to temperatures of millions of degrees. This causes it to glow with an intense flare of radiation, often outshining the combined light of every other star in the entire galaxy for several months. Astronomers can observe these brilliant flares across the universe, a telltale signature of a black hole's meal. It is a catastrophic and beautiful end, a star's death providing the fuel for a brilliant, transient beacon that illuminates the dark heart of its galaxy. This violent consumption raises a profound question about the life cycle of galaxies. How many stars have met this fate, and what does this relentless feeding tell us about the long-term evolution of the cosmos itself? That brilliant death of a star feeds a dark giant, but could these giants themselves be the very glue that binds the cosmos? The 14th secret ventures into one of the most profound mysteries in all of science, a possible link between black holes and the invisible scaffold of the universe, dark matter. We know dark matter exists because we can see its gravitational handiwork. Its pull governs the rotation of galaxies, keeping their outer stars from flying away, and its gravity bends the light from distant objects. Yet, for all its influence, it remains completely invisible, not interacting with light at all. For decades, scientists have wondered what this mysterious substance could possibly be. One intriguing, though increasingly unlikely, idea is that it is made of black holes. Not the supermassive ones we find in galactic centers, but a hypothetical population of smaller, primordial black holes. These would not be born from dying stars, but from the intense pressures of the Big Bang itself. In the first chaotic moments of the universe, dense knots of matter could have collapsed directly into black holes of all sizes, from the mass of a small asteroid to many times the mass of our Sun. If vast numbers of these primordial black holes were forged in the infant cosmos, they could, in theory, account for the gravitational effects we attribute to dark matter. They would be the perfect candidate, massive and completely dark, drifting unseen through the galaxy. However, while this idea remains a possibility for smaller black holes, the evidence has largely ruled out supermassive black holes as a source of dark matter. We simply don't see enough of them. The number of supermassive black holes we have observed is far too small to account for the immense amount of dark matter that must be holding galaxies together. Their collective mass is a tiny fraction of what is needed. Furthermore, their formation seems tied to the visible structure of galaxies, not the invisible halo of dark matter that surrounds them. So while the dark hearts of galaxies are ruled by dark matter's gravity, they are not the primary component of that dark substance itself. The search for dark matter continues, pushing us to consider even stranger possibilities, from exotic subatomic particles to flaws in the fabric of gravity itself. The true nature of the universe's hidden skeleton remains one of its greatest unsolved puzzles. These dark giants are not always solitary rulers. The silent heart of a galaxy can sometimes beat with a double pulse, a gravitational signature of two supermassive black holes locked in a cosmic dance. This is the reality when two galaxies collide. Galaxies are not static islands, they are dynamic systems that often drift together over billions of years, pulled by their mutual gravity. When such a merger occurs, the two galaxies do not simply pass through one another. Their stars are so far apart that they rarely collide, but their vast clouds of gas and dust slam together, triggering spectacular bursts of new star formation. And at the center of this cosmic firestorm, the two supermassive black holes, once the separate hearts of their own galaxies, are drawn toward the new combined core. They begin to orbit one another, forming a binary pair. At first, they are millions of light-years apart, but the dance slowly tightens. As they swing around their common center of gravity, they stir up the surrounding stars and gas, their immense gravity slinging objects away in a process called dynamical friction. This loss of energy causes their orbits to slowly decay, drawing them ever closer. For a long time, this is an invisible waltz, detectable only by its subtle effects on the motions of nearby stars. But as the black holes get closer, within a few light years of each other, the dance changes. They begin to interact with the gas and dust in their environment, carving out hollows in the accretion disk and potentially creating a periodic flicker in the galaxy's brightness. The final stages of this dance are the most violent and energetic in the universe. When the black holes close to within about 1/10 of a light year, their primary way of losing energy shifts. They begin to radiate gravitational waves, ripples in the very fabric of space-time caused by their accelerating masses. With each orbit, they lose a little more energy, spiraling inward faster and faster until they finally merge in a cataclysmic collision that shakes the universe. For a fraction of a second, the merger releases more energy than all the stars in the observable universe combined, all in the form of gravitational waves. This is the ultimate fate of these binary systems, a spectacular end that forges a single, even more massive black hole. Finding these binary pairs is a major goal for astronomers, a search for the telltale wobble or double signal that betrays the presence of two dark hearts where we expect only one. What would the sky look like from a planet orbiting a star caught in the gravitational storm between two such colossal objects? The final act of that cosmic dance is a collision that echoes across the cosmos. When two supermassive black holes spiral into their last, fatal embrace, they do not merge quietly. Their incredible masses, accelerating to a significant fraction of the speed of light, whip the very fabric of space and time like a spoon stirring a vast, invisible fluid. These ripples are gravitational waves, the 16th secret of these dark giants. The energy released in that final fraction of a second is almost beyond comprehension. For a fleeting moment, the merger outshines the combined light of every single star in the observable universe. But this brilliance is not in light, it is in the raw distortion of spacetime itself. The waves propagate outward at the speed of light, stretching and compressing everything in their path by a minuscule, almost imperceptible amount. By the time these waves travel millions of light years to reach us, the distortion is incredibly faint, a change in distance far smaller than the width of a single atom. Detecting such a subtle signal from the most powerful events in the universe is one of the greatest technological challenges in all of science. Our current observatories, like LIGO and Virgo, are exquisitely tuned to hear the higher-pitched chirps of stellar mass black holes merging. The merger of two supermassive black holes produces a much deeper, lower-frequency rumble, a bass note in the cosmic symphony that requires a different kind of ear. Future missions like the Laser Interferometer Space Antenna, or LISA, plan to open this new window to the universe. This ambitious project will consist of 3 spacecraft flying in a giant triangular formation, millions of kilometers apart, using lasers to measure the microscopic changes in distance caused by passing gravitational waves. Catching the signal of a supermassive merger would be a transformative moment. It would allow us to census the population of these binary monsters throughout cosmic history and witness the final, violent moments of a process that shapes the very galaxies we see today. What other cosmic cacophony awaits our listening, hidden in the quiet vibrations of spacetime? That iconic fiery ring, the first direct image of a black hole, revealed far more than just a shadow. The Event Horizon Telescope's portrait of the supermassive black hole at the heart of galaxy M87 gave us a precise cosmic measuring tape. The dark central void, the black hole's shadow, is not the event horizon itself. It is a silhouette, a region roughly 2.5 times larger than the actual point of no return, created by the black hole's gravity bending the light from its swirling accretion disk into a perfect circle of darkness. The size and shape of this shadow were predicted with mathematical precision by Einstein's theory of general relativity over a century ago. The image we saw in April 2019 matched those predictions almost perfectly. The bright, lopsided ring of superheated gas confirms another key part of the theory, the phenomenon of relativistic beaming. The material swirling around the black hole moves at nearly the speed of light, and the side of the disk coming toward us appears dramatically brighter, its light amplified by its incredible velocity, while the receding side looks fainter. This single, grainy image, a testament to human collaboration and ingenuity, provided one of the strongest tests yet for general relativity in an environment of extreme gravity. It confirmed that Einstein's description of gravity as the warping of space and time holds true even at the very edge of one of the most violent places in the universe. What other long-held theories of physics will be put to the test as we peer deeper into these dark shadows? Our own galaxy's quiet heart reveals a crucial truth about these dark giants. Not all supermassive black holes are active, brilliant quasars or jet-spewing monsters. The difference between a slumbering beast like Sagittarius, a star, and a raging quasar comes down to one simple thing: its current meal. This is the 18th secret. A black hole's activity level is governed entirely by its accretion rate, the amount of gas and dust it is pulling in from its immediate surroundings. Imagine a campfire. A quasar is a roaring blaze fed by a constant stream of dry wood. Our own Sagittarius, a star, by contrast, is a heap of glowing embers with only a few twigs drifting onto it now and then. It is not fundamentally different, it is just starved for fuel. In the crowded core of a galaxy, the primary food source is interstellar gas. When vast clouds of this gas are funneled toward the center, perhaps by a galactic collision or the slow churning of the spiral arms, the black hole feasts. The gas piles up into a vast, hot disk, and that furious accretion process unleashes the incredible power of an active nucleus. But when the immediate fuel supply runs low or is blown away by previous outbursts, the accretion disk shrinks and grows faint. The black hole's immense gravity is still there, but with little to no matter to heat up, it becomes quiescent or silent. It is a predator in a barren landscape, waiting for the next cosmic migration of gas to drift within its reach. This cycle of feast and famine is a natural part of a galaxy's life, a rhythm that can turn a brilliant beacon into a dark shadow and back again over billions of years. What cosmic event could suddenly awaken a sleeping giant like the one at the center of our own peaceful Milky Way? This violent cycle of feast and famine does more than just light up the cosmos. It may also hold the key to life itself. The very outbursts that can sterilize entire galactic regions might also carve out the safe havens necessary for complex life to eventually emerge. An active supermassive black hole in its quasar phase is a force of pure destruction on a galactic scale. The intense flood of X-rays and ultraviolet radiation, along with the searing plasma jets, can scour the inner regions of a galaxy clean. Any planetary system within thousands of light-years of such an event would have its atmospheres stripped away and its surfaces bathed in lethal radiation, effectively resetting the clock for life. This is a cosmic sterilization event, yet paradoxically, this same violence might be a necessary step for long-term habitability. The powerful winds and radiation blasting out from the active black hole push vast amounts of gas outward far beyond the galactic center. This process, a form of negative feedback, sweeps the inner galaxy of the raw materials needed to form new, massive stars. Massive stars live fast and die young in spectacular supernova explosions, which themselves are destructive to nearby planetary systems. By quenching this rampant star formation, the black hole's fury can create a more stable, quieter galactic neighborhood over time. It fosters the conditions for the gradual, peaceful formation of longer-lived, stable stars like our own Sun and the planetary systems that orbit them. The galactic habitable zone, a region where conditions are just right for life, might not only depend on a star's location but also on the past activity of the galaxy's central black hole. Its ancient outbursts may have helped create the calm, long-lasting stellar suburbs where life has the billions of years of stability it needs to evolve. Could the very violence that makes the universe dangerous also be the force that makes it alive? This ancient puzzle strikes at the very origin of cosmic structure. We see the intimate connection between a galaxy and its dark heart, but which one truly sparked the process of creation? Did a massive seed black hole form in the primordial darkness, its immense gravity acting as a nucleus to pull in the first clouds of gas, triggering the birth of a galaxy around it? Or did vast halos of dark matter first gather, pulling in ordinary matter to form a swirling proto-galaxy, whose dense center eventually collapsed under its own weight to forge the black hole? The evidence we have points toward a co-evolution, a dance that began almost simultaneously. In the early universe, the first stars were colossal, living short, violent lives and collapsing into black holes. These could have served as seeds sinking into the center of the young proto-galaxy. There, they would have merged and fed, their growth fueled by the rich gas reservoirs, even as their own energetic output began to shape that very same galactic environment. It is a feedback loop from the very start, a symbiotic relationship where each partner influences the other's growth. Yet, the discovery of fully formed supermassive black holes when the universe was less than 1 billion years old pushes the limits of this model. How could they have grown so massive, so fast, unless the seeds were unimaginably large from the beginning? This suggests that in some cases, the black hole seed might have indeed come first, a primordial giant born from the direct collapse of a vast gas cloud, a dark king that established its domain before the first stars of its galaxy had even finished lighting up. The answer is likely not a simple one, but a story with multiple paths, where the sequence of events depended on the specific conditions of a galaxy's birth. This fundamental mystery forces us to look back to the cosmic dawn, to a time when the first structures were just beginning to cast their shadows against the fading glow of the Big Bang. What will the next generation of telescopes peering into that deepest past reveal about the very first moments of this cosmic relationship? We have mapped the stellar corpses and the galactic giants, but a crucial piece of the puzzle has remained stubbornly absent. Between the black holes left by dying stars and the supermassive leviathans anchoring galaxies, there should exist a middle child, a class of intermediate mass black holes. These are the missing links, the cosmic stepping stones that could explain how supermassive black holes grew so immense so quickly. Theorists suggest these are the building blocks, the seeds that merged and fed to become the monsters we see today. But finding them has proven incredibly difficult. They are not massive enough to whip entire galaxies into a frenzy, nor are they born in the brilliant flash of a supernova. Their gravitational signature is subtle, a whisper in the chaos of a star cluster. The hunt has focused on two key locations: ancient globular clusters and small dwarf galaxies. Globular clusters are dense, spherical swarms of hundreds of thousands of stars, all bound together by gravity. In these crowded environments, stellar collisions and mergers could have provided the perfect conditions to grow a black hole of a few thousand solar masses. Astronomers search for the telltale signs, stars moving with unexpected speed around an invisible central mass. In several clusters, the motions of stars hint at a dark, compact object lurking at the very heart of the swarm. Similarly, some ultra-compact dwarf galaxies, which are essentially the stripped-down cores of larger galaxies, appear to house a central gravitational anchor far too heavy for a collection of stellar remnants. One of the most compelling pieces of evidence came not from star motions, but from a brilliant, fleeting flash of radiation. A tidal disruption event where a star was ripped apart was detected in a distant dwarf galaxy. The energy and duration of that flare pointed to a black hole of around 50,000 solar masses, a perfect specimen of the elusive intermediate class. These discoveries are like finding the fossilized bones of a prehistoric ancestor, confirming a predicted stage in the evolutionary chain. They suggest a universe where black holes grew hierarchically, starting from these intermediate seeds and merging over cosmic time to build the supermassive giants we know today. If these missing links are indeed common, what other cosmic nurseries are hiding them? And what stories do their quiet masses tell about the violent construction of the early universe? Those powerful jets screaming from a galactic core do not form by gravity alone. They are shaped and launched by an invisible force, a cosmic puppeteer whose strings are made of pure magnetism. This is the 22nd secret, the hidden role of incredibly powerful magnetic fields. The chaotic whirlpool of an accretion disk is more than just hot gas. It is a turbulent sea of electrically charged particles, a plasma. As this churning material spirals inward, its motion generates magnetic fields of staggering strength, billions of times more powerful than Earth's. These fields are not smooth and orderly. They become twisted and wound up by the disk's rotation, like a rope of energy being coiled tighter and tighter. This magnetic tension cannot hold forever. In a dramatic release, the fields snap and reconnect, channeling vast amounts of energy and accelerating particles to nearly the speed of light. The magnetic field lines act like the rigid walls of an invisible pipeline, funneling a fraction of the infalling plasma away from the disk and focusing it into two narrow, opposing beams along the black hole's rotational axis. This is the birth of those colossal jets. The entire system functions as a natural particle accelerator of cosmic proportions, far more powerful than anything we could ever build on Earth. The particles racing through these magnetic conduits are slammed and boosted to energies that defy belief, producing the high-energy radiation we detect as gamma rays and X-rays. Some of these particles, typically protons, can escape the jet entirely, becoming cosmic rays that travel across the universe. The next time you hear about a mysterious high-energy particle from deep space striking our atmosphere, it might have begun its journey in the magnetic maelstrom surrounding a supermassive black hole. How does an object defined by its gravitational pull become the universe's most efficient magnetic engine? A supermassive black hole can be violently evicted from its own galaxy. This staggering possibility emerges from the final moments of a black hole merger, when the emission of gravitational waves becomes intensely asymmetric. As the two black holes spiral together and finally collide, the resulting blast of gravitational waves does not always spray out evenly in all directions. If the black holes have different masses or are spinning at different angles and speeds, a powerful, lopsided burst of energy can be unleashed in one particular direction. According to Newton's third law, for every action there is an equal and opposite reaction. The recoil from this one-sided gravitational wave blast can literally kick the newly merged black hole clear out of the galactic core. This is not a gentle nudge. The kick velocity can reach thousands of kilometers per second, a speed far greater than the galaxy's own escape velocity. The black hole, this newly formed monster weighing millions of suns, is shot out into the vast, dark emptiness between galaxies, becoming a rogue, a wanderer without a home. For a time, you might see a bizarre spectacle, a brilliant quasar shining from the outer fringes of a galaxy, or even from the middle of nowhere as the black hole's accretion disk struggles to follow it, glowing fiercely before eventually fading. The galaxy left behind would be profoundly changed, its central gravitational anchor suddenly gone, its core stars left to drift without their dark master. What chaotic stellar dance would unfold in a galaxy that has lost its heart? The growth of these cosmic giants is not a local affair, confined to the dusty core of a single galaxy. Their fate is tied to the largest structure known to exist, an invisible scaffold that spans the entire observable universe. This is the cosmic web, a vast network of dark matter filaments that connects clusters of galaxies like glittering pearls on strings of invisible silk. Within this web, rivers of primordial gas, the leftover hydrogen and helium from the Big Bang, flow steadily along the dark matter highways. When these rivers intersect at the nodes of the web where multiple filaments meet, they fuel the birth and growth of galaxy clusters. And it is this same flowing gas that provides the ultimate feast for supermassive black holes. A galaxy's position in the cosmic web directly controls the growth of its dark heart. Galaxies isolated in the quiet voids between filaments have little access to this fresh, cold gas. Their central black holes starve, remaining quiet and relatively small. But a galaxy residing at a bustling intersection of the cosmic web is constantly being fed. Vast streams of gas flow into its core, driven by the relentless pull of gravity. This steady supply of fuel does not just form new stars, it funnels directly toward the waiting black hole, piling up into a brilliant, hot accretion disk that can power a quasar for hundreds of millions of years. The black hole becomes a cosmic engine running on the fuel delivered by the universe's largest scale structure. Its growth, and therefore its ability to shape its own galaxy through powerful feedback, is dictated by its address in the cosmos. The most massive black holes we see today likely grew to their immense size because their host galaxies were privileged to sit at the busiest crossroads of the cosmic web, where the rivers of gas flowed most freely. This reveals a profound hierarchy of control, where the invisible architecture of dark matter ultimately governs the feeding habits of the universe's most luminous and powerful objects. How many brilliant quasars are shining right now, their light a testament to the endless river of gas flowing from the cosmic web. The ultimate destination inside a black hole is a place where physics itself reaches its end. Past the event horizon, past the point of spaghettification, every path leads to the singularity. This is the 25th secret, the final frontier of our understanding, where the known laws of the universe cease to have any meaning. General relativity, Einstein's magnificent theory that describes gravity as the curvature of space and time, has guided us perfectly to this point. It predicts that all the mass of the black hole, millions or billions of suns, is crushed into an infinitely dense, infinitely small point. But infinity is not a physical concept we can measure or observe. It is a mathematical warning sign. It tells us that our theory is incomplete, that it has reached the edge of its domain. At the singularity, the curvature of space-time becomes infinite, and the equations of general relativity simply blow up, producing nonsensical answers. This breakdown is not a failure of the theory, but a signpost pointing toward a deeper truth. To comprehend the heart of a black hole, we need a theory that can marry the vast, smooth cosmos of general relativity with the fuzzy, probabilistic world of the quantum realm. We need a theory of quantum gravity. This would be a framework for understanding how gravity works at the smallest possible scales, at the level where space and time themselves might be made of discrete, vibrating units. Without it, the singularity remains the ultimate unknown, a blank spot on our map of reality. Some theories suggest it might not be a point at all, but a loop or a membrane, a place where the fabric of our universe connects to something else entirely. But until we can peer into that darkness with the light of a new physics, the true nature of the singularity will remain the most profound secret a black hole keeps. What strange new laws govern a place where density is infinite and volume is zero? The silent dance of stars around our galaxy's heart is more than a cosmic spectacle. It is a precision laboratory for the laws of physics. By meticulously tracking the orbits of stars like S2, astronomers are not just confirming the black hole's presence, they are using these stellar probes to map the intricate details of its gravitational field. Each star acts as a perfect test particle, its path dictated solely by the warping of space-time around the central mass. The slightest deviation from a perfect Newtonian ellipse, the subtle precession of its orbit, becomes a crucial data point. This is where Einstein's general relativity faces its most stringent tests. When S2 makes its closest approach to Sagittarius, a star swinging around at 3% the speed of light, it is moving through an environment of such intense gravity that relativistic effects become measurable. The star's orbit itself slowly rotates, its point of closest approach shifting with each pass, a phenomenon known as Schwarzschild precession. By observing this over many years, scientists can check if the observed shift matches the predictions of general relativity with exquisite precision. So far, Einstein's theory has passed every test, its description of gravity as curved space-time holding firm even here at the edge of a 4 million solar mass monster. These stellar orbits provide a map of gravity itself, revealing a landscape that matches our best theories while constantly challenging their limits. What other subtle whispers from these dancing stars will reveal a crack in our current understanding, pointing the way to a deeper truth? The tools we use to listen to the cosmos are about to be utterly transformed. The coming decades will see a new generation of observatories, both on the ground and in space, that will push our vision into realms we have only dreamed of exploring. The Laser Interferometer Space Antenna, or LISA, is perhaps the most ambitious of these projects. Instead of listening for the high-pitched chirps of stellar mass black holes, LISA will open our ears to the deep, rumbling bass notes of the universe. This space-based gravitational wave observatory, consisting of 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, will detect the slow, grand spirals of supermassive black holes as they circle each other for millions of years before their final collision. We will be able to hear the mergers of these giants across the entire universe from the very first epochs of cosmic time, giving us a direct census of how these dark hearts have grown and merged over billions of years. At the same time, colossal new eyes on the ground, like the 30-meter telescope, will give us an impossibly sharp view of the chaotic centers of distant galaxies. With resolution more than 10 times sharper than the Hubble Space Telescope, we will be able to watch individual stars whipping around the black holes in other galaxies, mapping their gravitational fields just as we do with S2 in our own Milky Way. We might even catch a supermassive black hole in the act of being kicked from its galaxy, or see the flickering light from a binary pair long before they merge. These new instruments will not just add to our knowledge, they will fundamentally rewrite the questions we are able to ask. What symphonies of gravitational waves and what violent stellar dances have been invisible to us until now, waiting for the right moment to reveal their secrets? Even the mightiest giants will one day fall. The final secret of these dark rulers is their ultimate fate, a destiny that unfolds on a timescale so vast it dwarfs the entire current age of our universe. While they appear as permanent fixtures in the cosmos, supermassive black holes are not eternal. Their reign, measured in trillions upon trillions of years, will eventually end in a whisper of radiation. This process is driven by Hawking radiation, that faint quantum leak we discussed earlier. For a black hole as massive as the one in our galactic center, this evaporation is an agonizingly slow drip. The more massive the black hole, the colder it is, and the slower it loses energy. A typical supermassive black hole would take around 10 to the 100th power years to completely evaporate, a number so large it has no meaningful comparison in human experience. The universe would be an ancient, cold, and dark expanse long before the first of these giants even began to feel the strain. But as a black hole slowly loses mass, a strange inversion occurs. The evaporation rate begins to accelerate. The smaller it gets, the hotter it becomes, and the faster it sheds its remaining mass. The final moments are not a slow fade, but a cataclysmic finale. When the black hole's mass dwindles to that of a small mountain, its temperature soars to billions of degrees. In an explosive flash of high-energy gamma rays and particles, the last remnants of the black hole vanish, returning all of its accumulated mass and energy back to the universe. That final burst is the last testament of a cosmic monarch, a fleeting spark in an otherwise dark and silent cosmos. It marks the end of an era defined by gravity's ultimate triumph, leaving behind a universe of scattered particles and fading light, a quiet epilogue to the age of galaxies and their dark hearts. From the silent, spinning whirlpools that twist space-time itself to the ancient, violent quasars that lit up the infant cosmos, we have journeyed through the 28 secrets of these dark giants. We have seen how they are not mere destroyers but galactic architects, their gravitational hands sculpting the very bulges of their home galaxies and regulating the birth of new stars. Their power to tear apart suns and launch jets that cross millions of light years is matched only by their profound mysteries, from the information paradox at their edges to the unknowable singularity at their core. They are the ultimate cosmic paradox, places of both immense darkness and blinding light, of absolute silence and the loudest collisions in the universe. They challenge our fundamental laws of physics and force us to look deeper into the fabric of reality. Each secret reveals a layer of their incredible influence, from dictating the potential for life in galactic suburbs to their ultimate, trillions of years-long fate of evaporating into a final, brilliant flash. These are not just astronomical objects, they are the dark, beating hearts of the cosmos itself. We would love to hear which of these cosmic secrets captured your imagination the most. Was it the stellar dance that revealed our own galactic monster, the possibility of rogue black holes wandering the void, or the profound connection they share with the invisible cosmic web? Share your thoughts below and subscribe to continue exploring the deepest mysteries of our universe.